All right. Hello. Thank you for joining me. Today I'll be discussing some considerations for efficient Fourier decoupling as part of the Happy Channel's Hello World series. Part of the series, I've been told, is that we should describe ourselves and say a little bit about what our work is. So my name is Johnsrude. I'm a finishing grad student at UCLA under the advisors Terence Tao and Wang, who is now at NYU Courant. The research projects that I've been involved so far, I have three preprints on the archive at the moment. I'll mostly be focused on this last one today, which is a preprint focused on proving a small cap decoupling theorem over the real numbers for the parabola with a logarithmic constant. The other projects I'll summarize briefly. One of them extends the result I just mentioned to the non-Archimedean fields and obtains a particularly clean and explicit constant with dependence that's reasonably optimal over the residue prime. And the third project with Zuolin at UCSD was a project to prove a restricted projection theorem over the p-adics in general dimension. Here, the restricted projection theorem is the result of Ganguo and Wang from the real numbers. And this was proved by first establishing a Fourier decoupling theorem over the moment curve over the p-adics. And I'll mention that these results also generalize to sort of general non-Archimedean local fields with a certain characteristic assumption. What I'll be talking about today all lies under the framework of the so-called decoupling problem. A decoupling problem takes the following form. We have a system of functions f theta, one for each theta as theta ranges over some set. The functions f are functions that take complex values on the plane and which are assumed to have a certain prescribed Fourier support. So the Fourier support of f theta is contained in theta. We'll be interested in orthogonality, higher order orthogonality properties of these functions, assuming certain configurations of the underlying sets. Specifically, we will be comparing the Lebesgue p norm, the LP norm, of the sum of these functions to the little LQ big LP norm of the collection of the f thetas. When q equals 2 and p equals 2, this is simple orthogonality in the case that the thetas are disjoint, orthogonality plus Plancherel. But under special configurations, we can in fact show much more. This decoupling constant measures the extent to which we can prove such an orthogonality inequality. Frequently, the kind of result one is interested in is something that is subpolynomial in the number of caps under consideration. So this constant will frequently depend on some underlying parameter, and we will be interested in optimizing that dependence. The standard example is to take the parabola, the truncated parabola in 2 dimensions, and break its delta neighborhood up into a bunch of little rectangles of dimension delta in the vertical direction and delta to the power 1/2 in the horizontal direction. We form this decomposition, and we imagine splitting a general function with this Fourier support into a bunch of pieces theta. These theta are important as they're the largest parallelograms that one can fit in this neighborhood. The decoupling theorem for this particular configuration, this configuration being abbreviated as gamma theta, is the result proved in 2014-2015 by Wang and Demeter, and that is that the little L2 big L6 decoupling constant for this configuration is subpolynomial in the parameter delta. It is effective in principle in the sense that one can carefully trace through their inequalities and figure out an explicit form for this, but many of the dependencies are rather bad. On the other hand, the exponent range for a result of this type is sharp, and it goes much beyond the previous known result. Classical techniques like Cordoba-Pfefferman tell you something like this when 6 is replaced with a 4. And then Wolff's original paper from 2000 proved a result when the 6 is a large number, something like 76, and there's a corresponding power loss as is necessary when the exponent goes beyond 6. I'll mention a couple of other results of this type, although there are a great many. One of them is by Guth, Meldog, and Wang from 2020, and that shows that this same decoupling constant can in fact be taken to be polylogarithmic in delta. This is important as it's known by a paper of Bolgan in 1993, who was not considering decoupling constants, but this result falls out of it, that the decoupling constant is at least polylogarithmic. And so this particular dependence is sharp up to optimizing the exponent and then optimizing whatever prefactor you have. This has been for the parabola. That's the sort of base case. There are a number of alternate cases that people have considered: general moment curves, paraboloids, cones, and so forth. And they have led to a wide variety of important results in analysis. I'll mention just a few. First of all, Diophantine solution counting for things like Vinogradov systems, local smoothing estimates for the wave equation, mean value estimates for exponential sums, Strickhart's estimates, restriction estimates, and then slightly more generally geometric measure theory, a la things like Kekaya estimates, and then also dynamics, which is a particular range of results I'm particularly excited about. Here, the recent work has been in the direction of understanding unipotent flows on certain symmetric spaces. This has been concerned with something called canonical decoupling so far, because the boxes that we chose are the largest boxes possible. There's an alternate version of decoupling called small cap decoupling over the parabola, small cap parabolic decoupling. The 1/2 in the exponent delta 1/2 by delta is now going to be replaced by a beta, for some beta between 1/2 and 1. And for that parameter, we're going to define the decomposition of the thickened parabola as a union over small caps gamma, where these gammas are now defined by taking vertical strips of width delta to the power beta and intersecting that with the little thickened neighborhood of the parabola. Geometrically, this corresponds to taking the original canonical caps and breaking them into rectangular pieces. This particular choice of decoupling problem turns out to be very useful for many different applications. It's somewhat still being explored, but I'll mention a few. One is short mean value estimates for exponential sums. There's also projection theory and dynamics, and solution counting. Solution counting is interesting in this context because canonical decoupling tells you exactly solutions to certain Diophantine equations, or some count of them, whereas with respect to the small cap framework, one has some estimates on the number of near solutions to certain Diophantine equations. The result for this particular configuration was obtained by Demeter, Guth, and Wang, and that is that the decoupling constant for this configuration, where now I have some critical exponent in physical space, that's 2 plus 2 over beta, and then the frequency norm is increased from 2 to some other exponent. It's convenient to take these two exponents to be equal to each other. And then because this guy is not 2, there's now a sort of power loss. This is the optimal power loss for this particular pair of exponents. We still have some subpolynomial loss, but this particular result is already strong enough to imply many interesting applications. The main result that I'm talking about today is that the analogous constant, small cap decoupling constant, can be taken to have the same power law, but with now a polylogarithmic lower factor. Here, there's a slight alteration where we've changed the frequency exponent to a slightly smaller number. That is not original to this work. That was separately obtained by a few other authors, I believe Guth, Fu, and Maldog. So the really interesting thing here is obtaining this subpolynomial factor. A couple of quick remarks. For one, efficient decoupling constants in this sort of form are important in certain applications. It may be less important for questions related to LP mapping properties of certain operators, but if you're interested in something like solution counting, these more efficient estimates might be important. There appears to be some way of using this as well in dynamics, but that's current work that I can't comment too much on. Secondly, this main result is in fact easiest to prove in the non-Archimedean setting for reasons that I'll explore later. In the model case, you should think of replacing the real numbers by the p-adic numbers. And lastly, the approach that we take here is likely to be a sort of first step in a result that's currently hypothetical, but is believed to be true, which is a logarithmic decoupling theorem for the cone. So currently, the best known ways to decouple the cone is to compare it with a cylinder, and that process is inefficient enough that you obtain all sorts of bad losses that we're trying to avoid here. And so this is likely to be kind of a first step in that direction. Okay. So I'm now going to talk a little bit about how to prove this efficient small cap estimate. There are many different ways of proving decoupling theorems. There's broadly sort of three approaches that people have taken. The original version of decoupling, the original approach, is the Bolgan-Demeter method. And the Bolgan-Demeter method is unlikely to work for us. And the reason is that the main kind of estimate that one uses, the critical estimate, is this kind of induction on scales quantity, where you bound the decoupling constant at scale delta by a product of decoupling constants at coarser scales. The idea being is that if you want to break a function that has support on this parabola into pieces that are this small, then what you should do is first break them into delta to the epsilon pieces, then delta to the 2 epsilon pieces, and so forth, all the way until you reach the scale you want. And the problem is that for reasons related to Bolgan's lower bound, each one of these factors individually could be rather large. So we know they can be polylogarithmically large. And if we multiply together all these quantities, you'll get something too big. And so we're not allowed to simply use this structure of an estimate, because each one of these individually could be too bad. That doesn't result in a sort of death of the estimate. The estimate is still true. And the reason is that you expect at most of these scales that these particular decoupling constants are inefficient. One expects that at most scales, the particular configuration of the function is not the worst configuration. That can only happen very occasionally. There's another variety of decoupling that's inspired by Woolley's proof of the main conjecture of the Vinogradov mean value theorem of efficient congruency. And those methods have similar issues to the Bolgan-Demeter one from the perspective of polylogarithmic losses. The general theme that we have to follow, if we're to avoid the problems I mentioned before, is that we have to exclude most of the function that we're decoupling from iteration. And the particular approach that's going to be efficient from this perspective is a high-low approach, and that's the third way that people do decoupling. I'm going to follow a particular method that was demonstrated by Larry Guth and Dominique Maldog. It is a high-low approach that involves many scales, just like induction on scales. But we're going to be careful about not iterating pieces too much. It's named high-low because there's a high and a low contribution on the Fourier side. And there's sort of two components to the Fourier decomposition. The first is to split the parabola up into canonical scale caps. Remember that we're trying to get all the way down to small caps. And then rather trying to go from canonical scale caps to small caps directly, which is known to not work, we instead consider a decomposition of the small caps into pieces that are near the middle and pieces that are far from the middle. So that's splitting each of these thetas into these theta superscript kappas. These are the low pieces and the high pieces. And the utility of this decomposition comes from the following two observations. First of all, the low pieces, the pieces that are in the middle, are separated from each other for distinct caps. They're far away from each other. And secondly, if I consider the high components, those are useful for when I pass to the square function, which essentially moves all these caps to be centered at the origin. And then when you have such a configuration, the high components are orthogonal to each other by virtue of geometry. And those are the basic two observations. Rather than thinking in terms of the Fourier decomposition, it's mostly convenient to think in terms of the physical side, so in terms of wave packets. I'm going to briefly review the method of Lariguth and Dominique Maldag, not because that's the part that's original in this, but because that's going to be important to understand where the improvements come from. So, okay, what goes on the physical side? Well, we represent each f theta, each piece of the function that comes from one of the particular caps. There's a standard trick which is decomposing this f theta into a sum of wave packets. So we represent on the physical side, f theta is a sum of pieces eta t times a scalar at. These eta t's should be thought of as the indicator of certain dual boxes to theta times a certain phase, because here we have to come from this box on the frequency side, so we have to have some phase corresponding to that. The wave packets have inverse scales to theta, so theta has delta by delta 1/2 as the components. These dual boxes are then going to have components delta -1 and delta -1/2. That's the first bit of the physical space geometry. The second one is something called a wave envelope, and that corresponds to collecting nearby wave packets into these wider boxes that have the same length but are broader. And these are called wave envelopes. You should think of this as essentially corresponding to taking a single point, looking at all the wave packets from a broader region of frequency space that pass through that point, and then taking the convex hull. In the particular approach of Guth-Maldag, this collection of wave packets undergoes a certain pruning procedure. So what you do is you take your original function f, and you first split it into the wave packets that have high amplitude, that have a lot of mass on them, and then all of the wave packets that have a small amount of mass. The stuff with a small amount of mass is going to be estimated separately, and then the stuff with a large amount of mass is going to undergo the iteration. The pruning goes on through every scale. We take the high mass wave packets, we gather them into wave envelopes at the next scale, so broadening in the transverse direction by a factor of 10, say. And then we ask which of these wave envelopes have high mass. If a given wave envelope has high mass, then we throw it into this new function, and then if it's low mass, we throw it into this function. And we keep going. And all the high mass envelopes keep going through the iteration, whereas the low mass envelopes undergo a separate estimate. Here, the superscript b and the superscript g from earlier correspond to good and bad. The bad contributions at scale k are the wave envelopes that overall have a small amount of mass, but all of its sub-envelopes have a high amount of mass, or are absent altogether. By virtue of this irregularity, where there's a high amount of mass for certain parts in the transverse direction and then a low amount of mass in other parts of the transverse direction, it follows that a certain square function associated to this bad part has high frequencies in the transverse direction because there's an irregularity. And that's the basic observation on the physical side. The upshot of this analysis is something that they refer to as a high amplitude wave envelope estimate. I won't step through it carefully, but it mimics the proof of the square function estimate for the cone in 2+1 dimensions, with the exception that we only include in this expression those wave envelopes that have high mass. I'll move along. How does this relate to the problem of obtaining logarithmically fine decoupling constants? Well, the remark is that once we've done this pruning, each one of these bad parts that got split off of the iteration has only a finite number of scales that have bad configurations. So decoupling, of course, can have some bad configurations by Bourgain's argument, but it turns out that for these particular guys, there's only a small number of scales where that kind of configuration happens. And so the general idea is that you can spend about log many, a factor of log to pigeonhole f down to a single one of these guys. Then once you have a single one of these guys, you can spend a polylogarithmic constant to ignore all the lower scales that are present in this fk. And then now that you have a single one of these with a single scale that's relevant, you can spend a polylogarithmic constant to decouple at a single scale. This is the broad structure of the decoupling estimate. Implementing this involves a few tricks. Some of these are standard, and then some of them are novel. Let me speak to the general sources of problems first that are already well known. First of all, the so-called high lemma, which comes from the Fourier considerations I mentioned a few slides ago, critically involves a Cauchy-Schwarz, and that loses factors that look like the ratio between two of our many scales. And so it's important that, however we set up the infrastructure of the argument, our scales need to grow sort of gradually. We can't have a huge gap between two scales. Secondly, a standard component of decoupling is a broad-narrow analysis. It's very important to consider contributions to the integral that come from two components of the function that are frequently separated from each other and are interacting in a common region of space. This analysis, as classically written, as you'll see in many standard texts, loses an epsilon, but it turns out that a slightly more careful analysis by putting a smaller constant on the iterated term fixes this and results in only a polylogarithmic loss. Another entry is that interpolation, just operator interpolation, can lose an epsilon. And the reason is that, at least over the real numbers, decoupling is not an operator inequality. So there's ways of doing some sort of interpolation, but they frequently lose a little bit. And the last source of problem is that pigeonholing can be inefficient. So there's many different ways to attempt to pigeonhole a function to take a certain regular structure. And depending on how you do that, you can lose a lot or only lose a little. All of these are standard problems that have been addressed in previous work, particularly the polylogarithmic decoupling theorem at the canonical scale. But there's also a more serious problem that has not been addressed before, and that is the interactions between parallel wave packets. And I'm going to illustrate this problem by asking a question, which is, for which scalar m is it true that when I take a certain wave packet t and then dilate it by a factor of m to get a big neighborhood around it. For which m is it true that when I take all of the wave packet functions corresponding to all of the wave packets that are far away from t, in the sense that they live or are concentrated outside of this big box, for which m is it the case that the sum of all of these parallel guys is extremely small in a suitable sense all the way along my wave packet? This kind of inequality is very important for the general framework of splitting off things as additive terms as opposed to multiplicative terms in order to avoid iteration. We need to be able to ignore all sorts of wave packets that could be near t. And in that case, we need to take some big neighborhood and use a sort of Cauchy-Schwarz. And in order to do that, we need m to not be too large. Otherwise, we're going to lose something too big. The general picture is one here. Here is this central wave packet. Here's a distant wave packet. It carries a certain wave packet function, eta t, on it, or eta t prime, I suppose. By virtue of the reals being Archimedean, this packet necessarily has a certain tail. It has a Schwarz tail. And what we need to arrange is that this guy is far enough away that this tail is not too large on t. It turns out that if we only use the fact that these guys are Schwarz, being the inverse Fourier transform of a bump function in Fourier space, if we only use that this guy is Schwarz, then we'll need to take this m to be sort of polynomial. And this epsilon comes from which Schwarz seminorm you're using. So if you quantify the amount of decay in some polynomial way, you get some inverse degree quantity coming out here. And so this is not good. The classical way of handling this is to replace wave packets with Gaussians, because those decay fast enough. This turns out to be very annoying because Gaussians on the Fourier side are also Gaussians. In particular, they don't have compact support. And that has, the Fourier side doesn't have compact support. And that's very annoying for all sorts of basic tricks that one does in Fourier analysis. And the general problem is that if you have some function which is compactly supported on the Fourier side, then you can't have exponential decay. And that's just by virtue of the Cauchy integral formula. This fits into a family of problems known as the Hardy uncertainty principle. I'll mention briefly that this problem that I'm illustrating is one of the reasons why p-adic methods are good, because in this setting we can actually just take our wave packets to be indicators, because on the Fourier side we get something else that's just an indicator up to a phase. The main novelty in this particular work is a special kind of wave packet, a Gevrey-class wave packet. And so it turns out that if you're willing to relax exponential decay to fractional exponential decay, that is something of the form e to the minus x to a power less than 1, then you're able to find such functions f that have compact Fourier support. And these are known as Gevrey-class functions, or Gevrey-class functions. A simple example of this is if you take a bump function, this is on the Fourier side, by taking this sort of standard construction where we have 0 and then the bump, which looks like some exponential of e to the minus x to a negative power, and then similarly at the other end of the bump, then it will turn out that the inverse Fourier transform of this bump has the kind of decay that we want. So for instance, if I take t to be 1/2, we get a minus 1 as the exponent up here. In particular, this includes the standard, or one of the standard ways of writing down a bump function that you would teach to analysis students. So in fact, our standard bumps, as we standardly define them, suffice. I had a problem that I mentioned earlier that motivated the use of better decaying functions. And I'll briefly mention that these better decaying functions are good from that perspective. So we needed some scalar that defined a big neighborhood around a wave packet. So let's take m to be this particular quantity. Notice it's polylogarithmic and not of the form delta to the epsilon, which is good. What happens when we consider the total contribution of parallel wave packets at a point? Well, up to rescaling, we're essentially concerned with this particular sum. Here I've chosen t to be 1/2. And then some simple analysis by splitting into dyadic contributions leaves us with an expression like this, which turns into this. Here I've left an indeterminate constant d that I'm allowed to pick to be very large. Here what we have is something polynomial in delta, polynomially small in delta, and then something logarithmic. This constant c is governed somehow by the geometry of R2, so it's just some universal constant. And so in particular, I can choose d to be very large, depending on the geometry of the plane, to get essentially a delta to the 1,000, also absorbing the effects of the logarithm in the process. And so we get the desired result. I'll mention general consequences. First of all, we have the desired real decoupling theorem that I mentioned earlier. Also, if I write down this argument over the p-adics, or more generally over non-Archimedean local fields of characteristic not equal to 2, then the analogous decoupling constant, here I've denoted that with the field in the superscript, takes this as an upper bound. I've written it down very explicitly to emphasize that the constants are not too bad in this case. Here I've got something polylogarithmic with an exponent 16 plus 6 beta inverse. I've also got a prefactor, which is not too bad. I've got a number p here. That's essentially the residue prime, with the exception that we have mixed characteristic and the residue prime is 2. In that case, I need to replace the residue prime with the prime 2 to the power of the extension. And it's just because 2 should really be invertible for these methods. In any case, I get something polynomial in that residue prime, and then a not too bad absolute constant. And that's the output of these methods. So thank you very much for your attention. Take care.